Welcome back, ladies and gentlemen. Here we go. We're going to talk about the next new topic, electric current. Before we get into actual specifics about electric current, I want to show something to you that it's going to be helpful later on. There's a way of looking at the relationship between between electrons and which are you can call them charge carriers and amount of charge. So we know that an electron has a negative charge to it, and it's equal to negative 1.6 times 10 to the negative 19 coulombs. That's one electron, the charge on one electron. Well, the interesting thing is scientists have never been able to come up with a measurement of charge less than that, smaller than this value. So this is often called the fundamental charge. Fundamental charge. And fundamental simply because, well, it can't be any smaller. If something has a charge to it, it would be at least this big in terms of the number of coulombs. Well, the charge on a proton would be positive E, essentially the same number, but the positive value, right? So essentially, coulombs. It is also essentially the fundamental charge. When you hear about the fundamental charge, typically you are just going to see the positive value. You don't. It's written without a plus or a minus, which really makes it a positive, but this is the smallest amount of charge that a particle, a stable, independent kind of particle can have. So an electron is a stable particle, a proton is a stable particle, but nothing can have a charge smaller than that if it's a sort of stable particle and doesn't have to be combined with anything else necessarily. Okay, now this is an interesting thing, this fundamental charge, because what we can say is we can relate the amount of charge of an object, Q, to that fundamental charge of E, and we can simply say, well, the amount of charge that an object might have depends on how many electrons it contains, or how many unbalanced electrons it contains, how many extra or fewer electrons it contains. So we could have any number, and that's just a number of charged particles right there, that guy. Number of charged particles, or sometimes called charge carriers, and of course Q is the total amount of charge, and now E would be this guy, the fundamental charge, which is just that number, right? So this is helpful because we're going to use this equation later on when we're dealing with electric current. You'll see how that works out. So now let's talk a little bit about electric current and get some things defined for us here. Electric current. The symbol for electric current is usually a capital I. And well, let's maybe try to define what current is. When charges move, it's called an electric current. So any moving charges, it could be moving positive charges or moving negative charges, any type. You would call that a current. Specifically an electric current, really. So this is interesting. Now, the word current, we often think of currents in water or maybe air currents as well. And, well, if there's a current in water, the water molecules are moving somewhere. If there's an air current, the air molecules are moving around somewhere. They're going somewhere. Same thing here with an electric current. The charges are going somewhere. And that does matter. Now, strictly speaking, what current is the rate. That's an important word in science. The rate of charges moving through something, through a substance. This is one way to define it. And so what we're talking about is this: the rate of charges moving. We're talking about charges that are moving. We have to look at the number of charges, or alternatively, the amount of charge is really a better way of saying that. So maybe not number of charges. How about amount of charge? And we're talking about the rate. So a rate is how quickly it's happening, and that means you're measuring time. So amount of charge divided by time. And so this is interesting because we see already that amount of charge, well, we know that's measured in coulombs, and time is measured in seconds. So we see the units of electric current are going to be coulombs per second. And there's an interesting thing here. Because of the early work of a French scientist named Ampere, and I'm probably not saying his name correctly, my pronunciation will be terrible, but because of his work with electric current, we define 1 coulomb per second to be 1 ampere. It's named after him, and there's how you spell it. Now, yes, it's named after a person. Like a Newton is named after a person. Now, here's how this works. You guys ought to know this. If you're naming the person, of course, you capitalize the A. But if you're naming the unit of measure, you do not capitalize the first letter. But when you abbreviate and use the short version, then you do capitalize the first letter. So an ampere, you might just say capital A for amperes. But there's another common thing that's done. We simply say amps sometimes. Same thing. Same thing. So 1 amp or 1 ampere is 1 coulomb per second. And coulomb is amount of charge, seconds obviously time. So now we need to look at this though and give it some thought, because we need some sense of an amp. Is it a large amount of current? Is it a small amount of current? We need some sense of what's going on here. So we're going to ask ourselves a question. How many electrons are needed to make up 1 coulomb of charge? And the reason we want to ask this question is because if we know the number of electrons that make up 1 coulomb of charge, we can say, well, then we know the number of electrons that have to flow through a material to create 1 ampere of current. So let's check this out. How's this going to work? Page 3 here. So some things we know. Since 1 electron has a charge, or it's equivalent to 1.6 times 10 to the negative 19 coulombs of charge. There's the fundamental charge basically coming into play, right? And yes, I recognize that electrons are negatively charged. That's okay. We're just going to come up with a number here. Now, another way of looking at this is to say that, well, there are 1.6 times 10 to the negative 19 coulombs in every electron. Or 1.6 times 10 to the negative 19 coulombs in each fundamental charge, right? Remember fundamental charge. There you go. So, That's helpful. However, we want something different. We don't want the number of coulombs per electron or per fundamental charge. We want the inverse of that. We want the number of electrons for 1 coulomb of charge. So let's take the inverse. All we have to do is look at this number and take the inverse. So that's when we do that, we start with coulombs per electron, and we're going to take the inverse and end up with electrons per coulomb. So basically, invert everything, right? Now, what about the number? We're going to invert the number. So inverting something is just as easy as doing this. So 1.6 times 10 to the negative 19. And essentially, this is the number of coulombs in 1 electron. So I have flipped it, it's true, but the number itself doesn't mean a whole lot to me. What I need to do is plug this into a calculator, and my calculator will have an inverse button. So I can actually get a number I can work with. It turns out I get 6.25, it's rounded just a tad, times 10 to the 18. So this is 6.25 times 10 to the 18 electrons per coulomb of charge. I need 6.25 times 10 to the 18 electrons to make up 1 total coulomb of charge. So now I also recall about electric current. One amp is 1 coulomb per second. And I've just said that it takes this many electrons, 6.25 times 10 to the 18 electrons, to make up that 1 coulomb. So I can combine those two things. 1 amp equals 6.25, there's a decimal right there, times 10 to the 18 electrons flowing through a material every second. It's supposed to be a C right there. So follow this again, right? So that it doesn't kind of get lost on you. Well, not that it would. We have the fundamental charge, or each electron has a charge of 1.6 times 10 to the negative 19 coulombs. So that's a tiny amount of coulombs in each electron. What we wanted was in 1 coulomb, how many electrons were needed. And so we found out that it's 6.25 times 10 to the 18 electrons in 1 coulomb that have to add together to make up 1 coulomb of charge. So since 1 amp is 1 coulomb per second, we can say that 1 amp is also 6.25 times 10 to the 18 electrons per second. That's what we're saying. Yeah, this number right here, 1 amp of current of moving electrons. So this is electrons per second. Now, it's not a number I need you to memorize. I just want you to think about that for just a moment. That number, you know what? That is a 6 and a 2 and a 5. And then how many zeros? Well, I'm going to move it once, twice, and then another 16 times. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. What does that come out to? There's million. That's million. That's billions. That's trillions. And that would be quadrillions. You know what this is right here? That's quintillions. I didn't even know there's a name for that. I had to look this up. 6 quintillion electrons every second if you have a current of 1 amp. Electrons every second. That's insane. That is a huge number. 6 quintillion electrons every second when there's a current of 1 amp. Wow. Okay, so now let's get it down to even more practical terms here. Let's look at an example of calculating the current. So here's a question for you. If 6.1 millicoulombs, that M is in millicoulombs, pass through a wire. Typically electric current is going to be sent through wires, right? If 6.1 millicoulombs pass through a wire in 4 seconds, 4.0 seconds, what is the current in the wire? Question. So, okay, how do we work this out? We might start with this 6.1 microcoulombs and kind of convert that to coulombs. We need that in sort of the base SI units. So 6.1 millicoulombs. Did I say micro a second ago? I'm sorry, millicoulombs. I'm going to change that to 6.1 times 10 to the negative 3 coulombs. Same value, same number. I just moved the decimal point 3 places for the milli prefix here. Now also, I need to realize something about current. Current is just the amount of charge divided by the time. That goes way back to the original sort of definition, understanding of current. Amount of charge divided by the time. And I have an amount of charge and I have a time, so it's relatively straightforward. 6.1 times 10 to the negative 3 coulombs divided by the time is 4 seconds. And I get an answer of 1.5 times 10 to the negative 3 amps. Capital A for amps, or amperes if you like to say the whole word. And that is rounded off a little bit. Each of these each of these numbers has only 2 sig figs, so my answer has only 2 sig figs. Fair enough. By the way, this is equivalent to 0.0015 amps, or equivalent to 1.5 milliamps. And the reason I want to show you that is because you'll see scientific notation. You'll see sometimes it's written out like this. Sometimes the unit has the prefix given on it, and you'll see milliamps, amps, something else with a different prefix possibly. Okay, so I have an answer in terms of the current flowing in the wire. Awesome. Now, one follow-up question. How many electrons flow through the wire during that time? Question. So here we go. Now we want to get from an amount of charge in that time to an amount of a number of electrons in that time, and here's where we're going to go back to that helpful thing right in the beginning of the video. This equation, this relationship between the amount of charge and the number of charge carriers. This is really the number of particles that are carrying the fundamental charge. And since we're talking about electrons, each one of them has that fundamental charge. So here we go. I'll write this down to begin with, and the answer I'm looking for is actually the N. I want the number, that's N right here. So I need to rearrange this, and it will become the amount of charge divided by the fundamental charge. Well, how much total charge is flowing here? Well, we just have the 6.1 millicoulombs, or 6.1 times 10 to the negative 3 coulombs. It should be in the base units, so I'll do that. And I want to divide by the fundamental charge. The fundamental charge is that charge on an electron, the 1.6 times 10 to the negative 19 coulombs. And you'll notice something interesting is going to happen here. We see that coulombs cancels, the units cancel, so we're just going to get a number, and that's what we want. We want the number of electrons, number of these particles. And when you do this math, 6.1 times 10 to the negative third divided by 1.6 times 10 to the negative 19, you get 3.8 times 10 to the 16 electrons. Let's put an E for electrons. That is how many electrons flow through the wire in this time. That again is a huge number of electrons. We're not talking about a large amount of current. This is a small current here. It's roughly 6 millicoulombs of, I said current, I'm sorry, charge. 6 millicoulombs of charge. We're talking about 1.5 milliamps of current. And look how many electrons are flowing with that small amount of current right there. 3.8 times 10 to the 16. That's a 3 and an 8 followed by 15 zeros. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So, the commas help me keep track of things. So there's million, billion, trillion, bazillion or something. No, million, billion, trillion, quadrillion. 38 quadrillion electrons. Oh my goodness. Okay, there are a few other things that you need to know about electric current. So we're going to wrap this up with just a few more ideas. So just like water flowing, water will flow as long as there's a gravitational potential difference. So think of a lake somewhere, and the lake's on a hillside. Okay, and there's another lake down here maybe, right? Well, there's a height difference between the two lakes, and if it's allowed to, won't water flow kind of down along a river to the lower lake? And the water will flow in the river as long as there's a difference in gravitational potential energies from this location to this location. So that makes sense because of the difference in height. There's a change in height right there. Well, that's water, and that's what water does. If there's a height difference, it will like to flow down to the lower elevation. And it will keep flowing as long as there exists that gravitational potential difference. Once the water gets down to this lower lake, it really doesn't want to go anywhere because there's nowhere lower to go, maybe, right? Now, charges will flow as long as there's what's called an electric potential difference. Charges are a little bit like water. Yep. I can spell, I swear. Charges will flow as long as there is an electric potential difference. This word, electric potential difference, or electric potential. It's very much like gravitational potential energy that causes the water to flow downhill. The charges will move as long as there is an electric potential difference. Think of it just like that. Whenever it exists, charges will flow and you get current. All right. Now regarding current, there are generally two ways to look at and talk about current. And this is, we're going to wrap up the video with this. This is something that kind of bugs me because the way most people do this, it's wrong, and everyone knows it's wrong, but they agree to keep doing it this way anyway. So there's a thing called conventional current. Conventional current. And this essentially is a flow of positive charges in the positive direction. I use that symbol for positive. Positive charges in the positive direction. Okay, fine. But think about, a metal wire. It's a good conductor, made up of all these atoms. Let's say it's a copper wire, made up of a bunch of copper atoms. The atoms are all kind of stuck together, but the electrons are free to move. So think of it, that's what makes it a good conductor. The electrons are what move, and the positive charges in the copper atoms, they're kind of stuck. They are not free to move. All those positives right in there, they don't have an easy time at all getting out of there. They're stuck in the nucleus. Takes vast quantities of energy to liberate things in the nucleus and free them up, and we're not dealing with nuclear reactions. So this is weird, and this is wrong technically, because positive charges aren't moving from one place to another. They're staying put, quite literally. They're not moving. It is the electrons that are moving. But this, the conventional current, is what everyone seems to use. Now, it turns out it doesn't matter. Your hair dryer and your phone charger and all these other things that use electricity, they still work. They work just fine. But it's not accurate, this idea of conventional current. Here's what's accurate. It's called electron flow. This is what really happens. In electron flow, you have the flow of negative charges in the negative direction. And that is really what happens. You have electrons which are negatively charged, and they move freely through all the conductors. And when we actually start looking at real circuits, we'll realize what we mean by positive direction or negative direction. It's quite easy to understand. But here's the issue. I have to teach this to you. I have to teach you conventional current, because that's what everyone seems to use and understand. Okay, well, just keep in mind, it works. You can use this and use this to talk about circuits and everything else. It does work. You just really need to be consistent. If you're going to use conventional current, be consistent in using conventional current all the time, and that's going to be fine. And that's what we will do. Your textbook will expect that. Any tests you take will expect you to use conventional current when analyzing circuits and whatnot. Okay, but please remember, this is actually what's happening. That's the real deal right there. But we are going to still use that. I know, that's life. Anyway, ladies and gentlemen, thank you for watching. I will catch you next time.